In 1989, a spacecraft flew past Neptune and picked up a signal that shouldn't have been there. A faint chemical signature in the planet's upper atmosphere that only makes sense if something is glowing up there, the same way the northern lights glow above Earth. Scientists suspected they'd caught the fingerprint of an aurora on an ice giant 3 billion miles from the sun. And then, for 36 straight years, nobody could actually prove it. Every other major planet in our solar system with a strong magnetic field, confirmed, photographed, studied in detail. Neptune sat there, the one glaring exception, its aurora reduced to a rumor nobody could pin down. Until James Webb finally did what no other telescope on Earth or in orbit had ever managed. Everybody, this is the story of what James Webb found when it finally looked at Neptune closely enough to end a mystery that outlasted an entire generation of astronomers, and what it discovered wasn't just an aurora. It was proof that this planet's entire magnetic environment works completely differently than anyone assumed, hiding in plain sight for over 3 decades. Let's go back to where the mystery actually started, because you need the full picture. NASA's Voyager 2 remains to this day the only spacecraft in human history to ever visit Neptune up close. It flew past the planet on August 25, 1989, at the tail end of its grand tour of the outer solar system, and it had one shot, one pass, moving too fast to linger, before continuing on its permanent journey out of the solar system entirely. During that flyby, Voyager 2's instruments picked up hints of something interesting happening in Neptune's upper atmosphere, specific chemical signatures consistent with auroral activity, the same basic physics responsible for the northern and southern lights here on Earth. When charged particles, usually streaming outward from the sun, get funneled by a planet's magnetic field down into its upper atmosphere, they collide with gas molecules and release that collision energy as glowing light, exactly the mechanism behind every aurora ever observed anywhere in the solar system. Every planet with a sufficiently strong magnetic field should, in theory, produce some version of this phenomenon. And by the time Voyager 2 reached Neptune, astronomers had already confirmed auroras on Jupiter, Saturn, and Uranus. Neptune was the missing piece, the last of the solar system's magnetized giants where nobody had actually captured direct proof. To really understand why this aurora mystery took 36 years to solve, you have to understand what an outlier Neptune has always been in the story of solar system exploration. Neptune wasn't found the way most planets were, by someone simply pointing a telescope at the sky and noticing something new. It was found through pure mathematics first. Astronomers Urbain Le Verrier and John Couch Adams, working independently in the 1840s, noticed that Uranus wasn't orbiting the sun quite the way the equations said it should, and they calculated that the gravitational pull of an undiscovered planet must be tugging on it from farther out. Based on those calculations alone, astronomers Johann Gottfried Galle and Heinrich Louis d'Arrest pointed a telescope at the exact patch of sky the math predicted on September 23, 1846, and found Neptune sitting almost precisely where the numbers said it would be. It remains to this day the only planet in our solar system discovered through mathematical prediction before it was ever actually seen. Just 17 days later, on October 10, 1846, British astronomer William Lassell discovered Neptune's largest moon, Triton, funding his own telescopes with a fortune he'd made in the brewing industry. Triton turned out to be one of the strangest moons in the entire solar system, the only large moon anywhere that orbits its planet backward, in the opposite direction of Neptune's own rotation. A retrograde orbit that strongly suggests Triton wasn't born alongside Neptune at all, but was instead a wandering object from the distant Kuiper belt, captured by Neptune's gravity at some point in the ancient past. For the next 143 years, that's essentially all humanity had to work with. A mathematically predicted planet, a strange captured moon, and whatever details astronomers could squeeze out of increasingly powerful ground-based telescopes staring across nearly 3 billion miles of empty space. Then, in August 1989, NASA's Voyager 2 became the only spacecraft in human history to ever visit Neptune directly, the final stop on what's often called its grand tour of the outer solar system, a mission that had already used the gravity of Jupiter in 1979, Saturn in 1981, and Uranus in 1986 to slingshot itself steadily farther out. Voyager 2's navigation during that Neptune approach was, frankly, remarkable. The spacecraft arrived within 22 miles of its precisely charted course and within 1 second of its scheduled arrival time. After a journey that had already taken 12 years and covered billions of miles, skimming just 3,000 miles above Neptune's North Pole, the closest approach any spacecraft has ever made to one of the solar system's outer planets. In the brief window it had, Voyager 2 transformed our understanding of Neptune almost overnight. It confirmed the planet actually has a ring system, something astronomers had only speculated about for decades. It discovered 6 entirely new moons that nobody on Earth had ever detected. It found supersonic winds tearing through Neptune's atmosphere at speeds up to 700 miles per hour, among the fastest winds recorded anywhere in the solar system. It photographed the Great Dark Spot, a storm system roughly the size of Earth itself churning in Neptune's southern hemisphere. And when Voyager 2 swung past Triton on its way out of the system, it found something nobody expected on a moon sitting at nearly minus 400 degrees Fahrenheit. Active geysers, spewing icy material more than 5 miles into the thin atmosphere above, making Triton one of the only geologically active moons ever documented anywhere in the solar system. Almost everything scientists currently know about Neptune's rotation period, its magnetic field, and its overall magnetosphere came from that single brief encounter. But Voyager 2 never went back, and nothing else ever went in its place. No follow-up mission to Neptune has ever launched in the 36 years since. Every subsequent observation of this planet has had to come from telescopes staring at it across billions of miles of space, and that's precisely the gap the auroral mystery fell into. Voyager 2 caught a fleeting, ambiguous hint of something glowing in Neptune's atmosphere during its one brief pass, and then human spaceflight simply left the question hanging, with no way to send anything back out to confirm it directly. The comparison to Neptune's neighboring giant planets only made that gap more frustrating for the researchers involved. Jupiter's auroras are so bright and so energetic that they've been studied in remarkable detail for decades, partly powered by volcanic material spewed out from its moon Io and funneled along Jupiter's powerful magnetic field lines. Saturn's auroras were mapped extensively during the 13 years NASA's Cassini spacecraft spent orbiting the planet, giving scientists a long, continuous data set to work from. Even Uranus, another distant, dim ice giant not too different from Neptune in basic composition and size, had its own aurora confirmed years earlier. Neptune sat there as the lone holdout among the solar system's 4 giant planets, the one place where theory strongly predicted an aurora had to exist, and where every attempt to actually catch it kept coming back inconclusive, decade after decade. Henrik Mellon, an associate professor at Northumbria University and the lead author of the research that finally cracked this case, explained exactly why this particular observation had proven so stubbornly difficult for so long. He said that, actually, imaging the auroral activity on Neptune turned out to be possible only because of Webb's near-infrared sensitivity, a level of precision no previous instrument, including Hubble, had been capable of achieving for a target this faint and this far away. That's not a small technical footnote. That's the entire reason this mystery survived for 36 years in the first place. It wasn't that scientists lacked the theory or the motivation to look. They simply didn't have a telescope sensitive enough to actually catch the signal until Webb came online. It helps to understand exactly what makes Webb capable of something. Hubble, one of the most celebrated telescopes in history, simply couldn't manage. Hubble, launched in 1990, was primarily built to observe the universe in visible and ultraviolet light, the same general range of wavelengths human eyes can perceive. Webb, launched at the end of 2021, was built specifically around infrared observation instead, tuned to detect the kind of longer wavelength light that's often invisible to human eyes, but carries an enormous amount of information about temperature, chemical composition, and faint emission processes, exactly like the ones responsible for auroras. Neptune's aurora, it turned out, glows overwhelmingly in a specific band of near-infrared light produced by charged hydrogen molecules called trihydrogen cations, a signature that ground-based telescopes and even Hubble simply weren't equipped to pick out clearly enough against the noise at a target 3 billion miles away. Webb's instrument built specifically for this range, the near-infrared spectrograph, or NIRSpec, was able to isolate that exact signature with a level of clarity nothing before it had ever achieved. In 2023, Mellon's team finally pointed James Webb's near-infrared spectrograph directly at Neptune, and the data that came back left no ambiguity at all. Distinct auroral emission, unmistakably present, glowing in the planet's upper atmosphere exactly where charged particles funneled by Neptune's magnetic field would be expected to strike. Mellon's own reaction to seeing it is worth repeating exactly, because it captures just how significant this moment actually was for someone who'd spent years chasing this specific target. He said it was stunning, not just to finally see the auroras themselves, but to see the detail and clarity of the signature, admitting the result genuinely shocked him. The findings were formally announced in March 2025, more than 3.5 decades after Voyager 2 first hinted that something was there. If a real mystery like this, 36 years in the making and finally solved with hard data, is exactly the kind of space science you come here for, subscribe now, because what Webb found next is even stranger than simply confirming the aurora existed, because here's where the story stops, being just a confirmation, and starts being a genuine surprise. When astronomers finally got a clear look at exactly where on Neptune's surface these auroras were actually occurring, the location didn't match anything familiar. On Earth, and on every other planet in our solar system where auroras have been confirmed, this kind of glow is almost always concentrated near the planet's north and south poles, because a planet's magnetic field lines typically funnel charged particles down toward those polar regions specifically. Neptune broke that pattern entirely. NASA's own description of the finding lays it out plainly. Instead of being confined to the planet's northern and southern poles, Neptune's auroras are located at the planet's geographic mid-latitudes, roughly equivalent to where South America sits on Earth's globe. Picture the northern lights suddenly appearing over the middle of a continent instead of near the Arctic Circle, and you start to understand just how unusual this actually is. The explanation traces directly back to one of Neptune's strangest known properties, a property scientists had already documented decades earlier but had never actually seen play out this dramatically before. Neptune's magnetic field isn't aligned with its rotational axis the way Earth's roughly is. It's tilted a full 47 degrees off-center, and it isn't even centered on the planet's core, sitting notably offset from Neptune's actual middle. That combination, a severely tilted off-center magnetic field, means the regions where charged particles actually get funneled down into the atmosphere don't line up with the poles at all. They land at these unexpected mid-latitude zones instead, a direct, visible consequence of Neptune's genuinely bizarre internal magnetic structure, something scientists had modeled mathematically for years, but had never been able to actually observe glowing on the planet itself until Webb's data arrived. This wasn't actually a complete surprise to planetary scientists, and understanding why takes you back, once again, to Voyager 2's original 1989 flyby. That spacecraft was the one that first discovered Neptune's magnetic field was this severely tilted and offset in the first place, and it found something almost identical happening at Uranus just 3 years earlier, during its 1986 flyby of that planet. Uranus's magnetic field turned out to be tilted an even more extreme 59 degrees from its rotational axis, also significantly offset from the planet's center. That similarity led planetary scientists to suspect for decades that both ice giants might share some fundamental characteristic in how they generate their magnetic fields internally, something genuinely different from the way Earth, Jupiter, and Saturn produce theirs. The leading theory involves the interior structure of these two ice giants specifically. Layers of electrically conductive fluid, likely a slushy mixture of water, ammonia, and methane under extreme pressure, sitting in a thinner, more turbulent shell around the planet's core, rather than in a deep, stable, well-organized layer the way Earth's molten iron core produces our comparatively clean, pole-aligned field. If that theory holds, it would mean Uranus and Neptune don't generate their magnetic fields the same way any other planet in the solar system does, a genuinely fundamental difference in how these two ice giants work on the inside, one that Webb's newly confirmed aurora location now offers direct, visible observational support for, rather than just theoretical modeling. That single detail reframes what this discovery actually represents. This isn't simply astronomers checking a box, confirming a phenomenon they always assumed was there. It's direct visual proof of exactly how strange Neptune's magnetic environment really is, a magnetic field so misaligned with the planet's own spin that it doesn't just tilt the auroras slightly off from where you'd expect. It relocates them entirely to a different part of the globe and now offers researchers actual observational evidence for a decades-old theory about what's happening deep inside an ice giant nobody has ever been able to look directly into. For context on just how unusual that placement really is, imagine standing somewhere in the middle latitudes of Earth, far from either pole, and looking straight up to see the aurora borealis glowing directly overhead. That's roughly the equivalent of what Webb actually captured happening on Neptune. A genuinely alien version of a phenomenon most people assume works the same way on every planet. And Webb's observations didn't stop at the aurora itself. While analyzing the same dataset, Mellon's team used Webb's instruments to directly measure the temperature of Neptune's upper atmosphere, and what they found added an entirely separate layer to the mystery. Comparing their new measurements against the readings Voyager 2 collected back in 1989, researchers discovered that Neptune's upper atmosphere has cooled dramatically since that original flyby, a genuinely significant temperature drop over the intervening 36 years. That's not a subtle, incremental shift. For a planet sitting nearly 3 billion miles from the Sun, already among the coldest, darkest environments in the entire solar system, a documented measurable cooling trend in its upper atmosphere raises real questions. Scientists are only just beginning to investigate. The leading candidate explanation involves something almost nobody thinks about when picturing Neptune, its seasons. Because Neptune sits so far from the Sun, it takes a staggering 165 Earth years to complete a single orbit, meaning each of its 4 seasons stretches on for roughly 4 decades at a time. Neptune only just completed its very first full orbit since being discovered back in 2011, meaning humanity has, quite literally, never watched this planet go through an entire seasonal cycle before in recorded scientific history. If Neptune's upper atmosphere genuinely does shift temperature meaningfully across a season that spans nearly half a century, the cooling trend Webb detected between 1989 and the present day could simply be this planet's version of autumn slowly settling in its upper atmosphere, a process happening on a timescale so vast that no human observation before Voyager 2 ever had the chance to notice it. And no observation after Voyager 2, until Webb ever had the sensitivity to measure it precisely enough to confirm. There's a second candidate explanation researchers are weighing as well, tied directly back to the same magnetic field oddities responsible for relocating the aurora in the first place. If Neptune's tilted, offset magnetic field genuinely does behave differently from a more typical planetary field, it's plausible that it also influences how efficiently the upper atmosphere retains or sheds heat over time, an interconnected relationship between the planet's magnetosphere and its atmospheric temperature that scientists are still working to model properly. A third possibility researchers haven't ruled out involves the solar cycle itself, the roughly 11-year rhythm during which the sun's own activity level rises and falls, subtly altering how much energy reaches every planet in the solar system, Neptune included, though the scale of cooling Webb detected appears too large to be explained by solar cycle effects alone. Right now, there's no single confirmed answer, only a real, measured, published temperature difference that wasn't expected before Webb's data came in, and a research team actively working through multiple competing explanations to figure out which one or which combination actually accounts for it. What makes this particular puzzle so compelling to researchers is that it's genuinely testable in a way many astronomical mysteries aren't. If the cooling trend really is seasonal, tied to that 165-year orbit, then continued observations over the coming years and decades should show the temperature trend either stabilizing or beginning to reverse as Neptune's season slowly progresses, giving scientists a real falsifiable prediction to check against future data. If it's tied instead to the magnetic field's unusual structure, researchers would expect the temperature anomaly to correlate directly with the auroral activity itself, rising and falling together as charged particles interact with the atmosphere in that unexpected mid-latitude zone. Untangling which explanation actually holds up will likely take years of follow-up observation. But for the first time in this planet's entire post-Voyager history, scientists finally have an instrument capable of gathering that data with enough precision to actually settle the question. Here's what makes this entire situation genuinely worth paying attention to going forward. Neptune remains the only planet in our solar system that a spacecraft has visited exactly once, briefly, during a single flyby nearly 4 decades ago, and never returned to since. Every single insight scientists have gained about this planet in the 36 years since that visit has had to come from telescopes staring across billions of miles of empty space, pushing the outer limits of what remote observation can actually achieve. James Webb just proved that limit is far lower than anyone expected. A mystery that outlasted an entire scientific career, waiting for confirmation since before most working astronomers today had even finished their education, got solved in a single, carefully targeted observing run, and it immediately opened up 2 entirely new questions. Nobody had properly answered yet why the magnetic field is tilted and offset badly enough to relocate the aurora to the planet's midsection, and why the upper atmosphere is measurably colder than it was when humanity's only spacecraft ever passed by. There's genuine momentum building to finally send something back. For years, planetary scientists across NASA, ESA, and the broader research community have advocated for a dedicated orbiter mission to Uranus or Neptune, something capable of doing for the ice giants what missions like Cassini did for Saturn, spending years in orbit rather than mere hours during a single flyby. The 2023 Planetary Science Decadal Survey, the document that helps guide NASA's mission priorities for the following decade, specifically named a Uranus orbiter as a top priority for the agency's next flagship class mission, a recognition that the ice giants remain the most underexplored category of planet in our entire solar system. No equivalent mission to Neptune has been formally funded yet, but the scientific case keeps strengthening with every new anomaly Webb manages to uncover from a distance. Every fresh puzzle, the misplaced aurora, the unexplained cooling, adds to a growing argument that remote observation alone, however powerful Webb has proven to be, can only take our understanding of Neptune so far. At some point, the case for physically going back becomes difficult to ignore. In the meantime, Mellon's team and other researchers around the world are continuing to use Webb for follow-up observations, tracking how Neptune's aurora and atmospheric temperature evolve over the coming months and years. Because Webb isn't a one-time flyby spacecraft the way Voyager 2 was, it can return to Neptune again and again over the course of its operational lifetime, building the kind of longer-term data set that a single 1989 encounter never could have provided. That's arguably the most important shift this discovery actually represents, not just solving one specific 36-year-old question, but proving that Neptune has finally, genuinely entered an era of sustained scientific observation, rather than depending entirely on the fading memory of one 12-year-old spacecraft encounter and whatever secondhand chemical clues it managed to catch on its way past. Neptune has always had a reputation as the quiet, distant afterthought of the outer solar system. The last stop before Voyager 2 permanently left planetary space behind, headed for its own eventual crossing into interstellar space decades later. What Webb just proved is that this planet has been sitting on a decades-old mystery this entire time, hiding in plain sight, simply waiting for an instrument sensitive enough to finally catch it glowing. And the fact that solving one 36-year-old mystery immediately handed researchers two brand new ones suggests this distant blue world still has plenty left to reveal if humanity keeps pointing the right instruments its way. If real solar system mysteries like this, the kind that take 36 years and a next-generation space telescope to finally crack, are what you come here for, subscribe and turn on notifications, because between the misplaced aurora and the unexplained cooling, Neptune is nowhere near finished surprising us.